Ah, that doesn't quite get in the top. Yeah, it gets it in enough. Okay. I wonder if I can I tilt this up? Ah, maybe yeah, did I just, can I tilt it a bit? No. Okay. I messed it up. Oh, well, people will hear me read it. Okay, so I think, so last year I did this thing and I did the video and I had the blackboard and everything. And I seem to remember it was much fuller. So maybe I covered more stuff last year, but I don't think so. I think I mean, okay, at the end when we were doing graph algorithms, I got really bored with graph algorithms, so I stuck in things like group testing and pattern matching and fun stuff for me that I didn't do this year. But I didn't think it was that. Maybe I just wrote more details last year. But anyway, those videos, I think you can find the videos from last year, right? Is this recording? Yeah, this is recording. I have to start this thing. Okay, hello? Anybody there? Can anybody, has anybody seen the videos from last year? They're also on the YouTube channel. Oh, okay. So they should be. So I'll post somewhere, I'll post the link to the YouTube channel that has all the videos from last year. If you go to the end, I mean, if you look at stuff and you're like, I have no idea what this is, I've never heard of this, it's probably because it's something I threw in last year that we didn't do this year. I think almost everything we did this year, we did, not sure if we did everything this, I'm not sure if everything we did this year we did last year. Anyway, okay, so let's just zip over what you should know, okay? So remember there was this clink versus boom thing where I said there are easy problems and hard problems, and you can't say I'm not interested in hard problems because I don't want to waste my time trying to do something that nobody can do. Like people for 50 years have been trying to do this stuff and nobody's got anywhere. I just don't want to know about it. And remember I said you don't have that option because there are hard problems all around us. And if you take an easy problem and you just tweak, you change one number from a 2 to a 3, and it becomes hard. So there are things, and is this going to show up on the final exam? Yes, probably. Where, like you change something very slightly and it goes from being easy to hard. And so you can't, so the two things you have to remember is hard problems are everywhere. You can't avoid hard problems. You have to learn how to recognize them, how to deal with them. Although mostly dealing with hard problems is going to be Algorithm Norbert's course. The other thing is it's fun. Like you go over and you can have fun with hard problems, and you can also you have cryptographic applications. So the lessons are, first, hardness is unavoidable and you don't want to avoid it anyway. And the other thing is you can't just pattern match. You can't just think, oh, this looks like a problem I've seen before. Yeah, well, okay, it's an exam, but I can try to make it some fun. For me, not sure. Okay, so I think they're cute questions. I've come up with the questions, and I think they're kind of fun. I mean, to the extent that an exam question can be. Okay, so the two things are, don't just pattern match. Don't just think, oh, this looks like a such and such question, I'm going to do it with it. Oh, I've seen a problem like this and it was solved with greedy algorithms. Blah, we do it. And be like, no, because remember I had that thing where you said, okay, partition it into increasing subsequence, greedy algorithms. find the longest increasing subsequence, dynamic programming. Okay, you can't just think, oh, this looks like a problem I've seen before, I remember the solution, I'll just write down the solution for the version I've seen before and hope that I will get most of the marks because, you know, if the problem hasn't changed much, maybe the solution doesn't change much. That strategy doesn't work. What else was there in Clink versus Boom? So I mean, that was the first time we saw Hampath, right? So we saw like, ooh, you have Eulerian cycles and Hamiltonian cycles, and one is easy and was done like they asked Euler and he just did it, and then Hamiltonian cycles is like hundreds of years later, we still don't know how to do it, and we think there is no polytope algorithm. Okay, so then we started with divide and conquer, and the first thing we did, because I didn't want you to get the impression that divide and conquer, we're going to start with the easy stuff. We're going to start with, you know, weak techniques because all you do with divide and conquer is sorting. No, so I didn't want you to think that. So we started with graph coloring, which is hard. So we did this coloring planar graphs where you have separators and you can split it, and I'm sure everyone remembers that because I wanted to sort of shock you right at the beginning of the course. And because that was still, when I did that assignment, it's still in the time frame, in the window when you can quit the course and get your money back. So anybody who was like, oh, I'm not sure I want to take this course, would be like, okay, well, this is sort of what it's going to be like, and then they had a chance to escape. So the people who didn't escape, it's like, well, you were warned, fair. So coloring graphs. So you probably remember how that went. Then we did Euclid's algorithm, which isn't a divide and conquer algorithm, but it was sort of, you know, a nice, you know, what is an algorithm, you know, historically the oldest algorithm. And it got us into talking about models of computation, because you think, okay, well, how hard is it to do an arithmetic operation? And we're talking about the complexity of adding, complexity of multiplying, because, you know, you have the number of steps, you know, when you have Euclid's algorithm, you're saying, does this divide that? And take modulus, take something A modulo B, you say, okay, how is it? So you count the number of steps, but that's assuming that this is constant time, and it's like, okay, if it's human being, it's not actually constant time. So you're talking about the models of computation. This got us into talking about Karatsuba's algorithm and how hard is multiplication. Remember, so down we finished talking about Kolmogorov complexity, and I mentioned that Kolmogorov was the person who made that conjecture that multiplication takes quadratic time, and Karatsuba in one of his seminars, and Karatsuba went away and proved it, and then Kolmogorov sent the proof in with Karatsuba's name on it. And then we did Strassen's matrix multiplication, where you cut it and you sort of do this sneaky thing where you, remember Karatsuba, you have the two numbers, you cut them each in two, and then instead of doing 4 multiplications, you do 3. And then with Strassen's, you take the matrices and you cut them in 4, and then instead of doing 8 multiplications, you do 7. Now, with Karatsuba, it's fair for me to ask you to memorize the formulas for Z0, Z1, and Z2, because they're easy. I mean, you can sort of recreate them. I am definitely not going to ask you to memorize the formulas for the M intermediate, the computations to compute the intermediate matrices, the MIs for Strassen's, because that would be sick. I don't think I know anybody. Maybe Strassen has them memorized, but I don't know Strassen. So it's probably fair for me to say I don't think I know anybody who's actually memorized those. Then there was the fast Fourier transform. If anybody has questions while we're going along, please post them in the chat, and I'll try to, actually, if I close the chat, then I see, then a little flag will pop up, and I will see that there's a question. Otherwise, yeah, maybe it pops up anyway, or like click the raise hand or something. We did fast Fourier transforms, so yes, you can use the lecture notes. I was thinking about it. Yeah, that's fair. So in fact, I guess even if I'm trying to talk to somebody to get this Respondus lockdown browser, blah blah blah. I don't know if I'm actually going to do that. But if you've downloaded and you have it in a PDF, then I guess you can actually just have the lecture notes, and you can also do a search, because I never got around to adding an index, which LaTeX does a nice index, but I haven't got one for the lecture notes yet. So you can just search. And click and jump and things like that. So you don't have to print it, because I would feel bad for the environment if I made 99 people print nearly 200 pages of lecture notes each. So please don't print it. Okay, fast Fourier transform. So yeah, you can have the lecture notes. Fast Fourier transform, you do not have to know. Okay. I think I promised when Max taught it in the lecture. I actually did the lecture notes for it, partly because I never saw it when I was an undergrad, and I have sort of a very shaky relationship with it. So I thought it's actually time, if I'm making you see it, it's time I finally learn it. I'm not sure I did learn it. I knew it, I understood it when I finished writing that chapter in the lecture notes. So I definitely know it better than I did at the beginning of the course, but I'm still not going to test you on it. Asymptotic bounds. So this is all that best case, worst case, average case, blah. But key thing to remember is worst case is not big O. It doesn't mean the best case, worst case, average case, and big O, theta, big omega, little o, these are orthogonal things, right? Big O is like at most about, little o is sort of less than, about, theta is like more or less about, big omega is at least about, little o is bigger than, and stuff like that. But you can say, like, in the best case, we use at most about, or at least about, right? These are so big, like big O is an upper bound, big omega or O or little o, or big omega or little omega is a lower bound, right? It's just saying, and then theta is saying, okay, within a constant factor, we have a tight bound. So asymptotic bounds, know that stuff. Sorting, and also the master method or master theorem or whatever you want to call it. So this was, I don't know if that was in sorting or if that was in asymptotic bounds. And my marker is dying right at the end of the course, finally, the black. Everything else is good. Maybe the blue is no, even the blue is fine. Sorting, so analysis, so we did sort of, we didn't just do merge sort and quick sort. Remember we said things like, okay, best case analysis, for example, insertion sort. What's the best case for insertion sort is actually linear. Remember, because it's, if the things are sorted if you're given the list sorted in reverse order, then it's actually just linear, because you always insert the things at the front. And then we were saying, okay, so we did merge sort, and then we did quick sort, we did quick select. And so this is how we did the average case, and we got a bit of randomization in there and stuff like that, which is one of the learning objectives of the course, I think. Okay. Questions? No, I think we're still, no, yeah, okay, we're still good. Okay. Greedy algorithms. So the thing is, like, I don't want the final to be a surprise. can you more or less figure out what's going to be on the final? Will there be a question about greedy algorithms? Yes. Is it likely you're going to have to write something that goes like, before we take any steps, our empty sub-solution can be extended to an optimal solution. Assume that after I steps, blah, blah, blah. I mean, yes, it's quite likely that you're going to have to write that, or at least know that, or because we've done it ad nauseum. There was a reason for that. I want you to know that. And it's not just because greedy algorithms are really useful. That's quite likely. I wouldn't be surprised if something like that showed up on the final. I'm not making any promises one way or the other. Look, will there be a question about greedy algorithms? Yes. Will there be a question about divide and conquer? Yes. Will there be a question about dynamic programming? Yes. Will there be a question about NP completeness? Yes. Will there be a question about graph algorithms? Yes. Will there be a question about diagonalizations? No. Okay, I'm letting you off the diagonalizations. But am I going to hit these? Yes. And the thing about I figure it's a course is 3 months, so you have 1 hour for each month. But look, it's not that. It's 1, 2, 3, 4, 5. 5 topics. I mean, that's not, you could get half an hour for each topic. You haven't seen the questions yet. You're just making that assumption on the basis that they're my questions and I don't ask easy questions. But maybe I do on finals. Okay. I didn't in the past 2 years, but I think the questions this year are easier than the past 2 years. So I'm also thinking, I think they're easy. I haven't, I have a selection of questions and maybe I'm going to throw some away, or maybe I'm going to give 1 or 2 of them might be bonus or something like that. But I think the course has been a reasonable algorithms, 3rd-year algorithms course for pretty much any university. Reasonably hard, but not to the extent that if you showed somebody this list of things we've covered, almost anywhere in the world, they'd say, yeah, that's a solid, good 3rd-year algorithms course. I want to be able to, if I show somebody my final exam, they'll say, yep, if you can pass that final exam, you have a good working knowledge of 3rd-year algorithms. No. So the thing, no, you won't have to program. Would we have an extra 5 minutes? Yay, I'm still thinking about I'm still thinking about the details. I'm not sure, maybe it'll be 9 to 12, maybe I'll give you a little bit extra time because there doesn't seem to be an exam that afternoon. Does anybody have an exam that afternoon? I mean, I know there are only, how many of you are there here? 10. So, 10% of my class. Does any of this 10% have an exam that afternoon? Anyway, if somebody's watching this recording, email me and say, okay, you have an exam that afternoon. Otherwise, I might give you a bit more time. If it turns out, I have to admit that the exam is kind of fun. I usually send my exams to Alex and Norbert, and then sometimes if they come back and say, no, this question is ridiculously difficult, or if they actually say they can't do it or something like that, then I tone it down a bit. I can't really do that. I mean, there are, last year, yes, I gave people between 7 in the morning and midnight or 9 in the evening or something like that. But this year, we're supposed to be back to, you write a synchronous final, etc. So things are supposed to be getting back to normal, and they told, I have an exam. I was given the morning slot on August 5th. So that's rough. If you're on like the other side of the Pacific. It's also rough if you're on this side of the Pacific but on the West Coast. Then it's kind of annoying, because that could be like, I guess it's actually really, really bad if you're in Hawaii or something. Because then it's not in the evening, it's like it's like 1 in the morning or something crazy like that. I don't know. I mean, does anybody know what the other professors are doing? Like there's a 31-36. I know last year Alex also gave people 24 hours. Or he gave people like from the start, yeah, I think he gave them 24 hours, and I just gave them from the 7 in the morning to 9 at night or something like that. But anyway, okay. I'm curious. I think the Dal's policy of inclusivity precludes me calling a time zone weird. I am not allowed, so okay, if you are in a weird time zone, to email him. I don't think I'm allowed to say this whole strip of the earth is a weird time zone. So to try to not be very centered on Halifax, I'm not going to say that. Okay, what? I'll think about it. Like I might do what I did last year and say, look, okay, people can have. I might. I mean, in that case, I'll add a bit more to the exam to make it reasonable for a longer time frame. I'm trying to get back to normal. I don't want it to be, but maybe something like that. I'll think about it. I'll write the exam and then look at it and think. I'll write the exam, I'll send it to the TAs and ask them how long it takes for them to do it. If they come back and say, because usually the factor is something like, if we're supposed to multiply by like times 10, whatever it takes us to write the answers, and times 4, whatever it takes our TAs to write the answers. So it's a 3-hour Brightspace exam that we can take anytime during exam week. But in that case, I mean, are they doing this weird thing where you have a bank of questions and it will select their questions randomly and blah, blah, blah? I don't really like that. It's not. Okay, so for example, I do not do multiple choice. I mean, okay, I do multiple choice if it's like that easy, like apply the master theorem thing, like is this big O of this, is this big O? Like I do multiple choice for that kind of stuff. But for algorithm design, it's too painful to design the questions. One last test scheduled for during exam week, where it's a scheduled breakaways. Yeah. So I mean, the nice thing about having a final, I mean, it's bad having an online final, but the nice thing about it, actually, okay, we should get, the nice thing about having a final is, I haven't really been trying to, I mean, I can't catch people cheating this year. I mean, you can go through, you could have somebody else do the whole course for you and get credit from me. It's like, fine, okay, we're in a pandemic, that's not I can't do anything about that. In a normal year, it's like that you're writing the final and you have your student card with your photo, and so people are like, yeah, okay, fine, you could get like a doppelganger to write the final for you. But you know, there are checks in place, and that's why we have this policy usually that you have to pass the final to pass the course. So that even if like people cheat, then there is this final check that you actually did learn everything. So my priority this year has not been to make sure people are not submitting, people are not copying and stuff like that.